Well, we are on to surface area. Fun stuff. So as promised in previous videos, we're going to go pretty mellow with the surface area. We'll just make a couple videos here. We'll keep it mild. I'm not even going to do the proof. I don't think you want to hear about the slant heights of cones and more partitions and stuff like that. Like, hey, don't worry, that stuff will come back. But let's take a section off here and let's just jump right to it. So surface area. So the area of a surface of revolution. No, more surfaces of revolution. Yeah, I think we're about done with that sort of stuff. This should be it. So one more thing to remember. So let f be a non-negative function with a continuous first derivative on the closed interval from a to b. The area of the surface generated when the graph of f on the closed interval from a to b, that's integrals too, is revolved about the x-axis. So, okay, so surface area about the x-axis, everything needs to be in terms of x's. Just like from before, you had to remember that with, discs and washers versus shells. We had to know which one goes with which. So for surface area, in terms of x's, about the x-axis. Let's get it. Now, look at the formula real quick. The integral from a to b, there's the arc length. That's just arc length. So the only thing we're doing is we're just adding in 2 pi times f of x into our arc length formula. So it's the same formula, just with the 2 pi and the f of x, which means we're going to be able to create maybe some u subs, or things will cancel out a little bit better than before, where arc length had to be completely cooked up. Surface area, not quite as much. So let's just jump into a problem and let's get after it. So the graph of some function f, which is equal to 2 times the square root of x, on the closed interval from 3 to 15, is revolved about the x-axis. Determine the area generated. All right. Well, I'm going to write down the formula right below. It's always good practice to write it a few times. And I write it as SA. No stress. I just like to make sure to differentiate the difference between a length, like the position function, which we use as S. And I just write SA. Your book writes S. Capital S. I put in SA. So, I do what I want. You do what you want, kind of. Just be right. And then I write my formula different. I yank that 2 pi out because I don't want the 2 pi inside the problem. And then we're left with f of x times the square root of, you mean our arc length formula. There we go. So, again, like that. It's 2 pi times our arc length formula, but inside our arc length formula, we just multiply by f of x. And they should seem fairly similar. It's almost similar to like shells and stuff, that 2 pi. It's different, though. It's not the same thing. All right. Let's run through it. So if we're going to do this problem, we want to find out what it is. Since we're going about the x-axis, we're all in terms of x's, we're good to go. Just like arc length, our first job, find the derivative. So we take our function f of x, and we find its derivative. I'm jumping this step. Hopefully, I don't know how you would get to Calc 2 and not know the derivative of the square root of x. You know what I mean? If so, good luck this semester. Got a lot of work to do. And then before we plug it in, we know it's squared as well. So let's square it, removing noise, and we just get 1 over x. Cool, let's go. I think we're ready. So we can say this is 2 pi times the integral from a to b. Well, where's a, where's b? A, b, we're good to go. 3 to 15. Our function is 2 times the square root of x. And now we have 1 plus, and now, why did I make my square root so long? There's not that much in there. And now we want to put in our f prime of x all squared, which we found over here to be 1 over x dx. Woo! Let's go. Let's go. Integral. A little bit of algebra, and this thing's going to fall out nicely. So first, noise. Let's get rid of it. Let's get that thing written as 4 pi outside of here. You know what I mean? From 3 to 15. And now we have the square root of x times the square root of, wait a second. Did we just have a square root times a square root? If you have a square root times a square root, doesn't that mean it's the same thing as just one big old frickin' square root? It does. It does. We're good. Let's go. So we have 4 pi times 3 to 15 of the square root of x times 1 plus 1 over x dx. Now it's going to be solvable. It's going to be a real simple U sub. Well, I guess, quotes U sub. There's absolutely no reason to do a U sub on this, but so we bring it in. That's x plus 1 dx. Tell me, there is no reason to do a U sub here. None. But I'll do it anyway because we're still kind of getting used to this. All right, let's do a U sub. I don't know x plus 1, so we'll say u is equal to x plus 1, and that means du is equal to dx. So let's get it. 4 pi times the integral. Since we're doing a u sub, that means we need to change our bounds, so I'll wait to do that. I'll wait to do the bounds until we're done, and then instead of x plus 1, we write in u, and instead of dx, we write in du. Now we just have to go and plug our numbers in. You know, when x is equal to 15, what's 15 plus 1? Yeah, u is equal to 16. And then when x is equal to 3, I'm pretty sure you know 3 plus 1, and u is equal to 4. Hey, let's get it. So now I'm going to get that thing all freaking derivative ready. I'm going to call it the 1/2 power, so it makes it a little simpler to do our power rule. So we have 4 pi times. Now here comes the integral. We're going to add 1 to our exponent. That's 3/2. And now we're going to multiply by its reciprocal and then evaluate from 4 on up to 16. So let's get them constants out before we go. Was that 8 pi over 3 times something to the 3/2 power minus something to the 3/2 power. And those somethings, yeah, you know, it's 16 and 4. Now for those of y'all that are doing your work at home, getting prepped, you know, you got a midterm coming up. Shoot, if you're in class, you know, you got tests coming up. Are you practicing with a calculator that you're not going to have on tests? How's your number sense? Can you solve this? Because this is not tough. Maybe you don't see it. And that's one thing. But this isn't tough to evaluate this. You got the skills. Now we just got to see it. Or just practice with the calculator, and then when you take a test in class, you just fail that problem. Yeah. Because we don't know arithmetic. So here we got 8 pi over 3 times. And then you're like, well, how do I do this? Well, isn't 16 4 squared and 4 2 squared? And the raised to the 3/2 power. Don't these 2's just cancel out? Isn't that just a multiplication? Isn't 2 times 3/2 3? Yeah, buddy. So what are we left with? We're left with 8 pi over 3 times 4 cubed minus 2 cubed. Yeah, you can do this now. That's 64 minus 4. So this is 8 pi over 3 times 60. And that's going to be what? 480 pi over 3. Does that go in evenly? Yeah, of course it goes in evenly. Because your teacher's stupid. Sorry. Why would I make bigger numbers? Why would I do that? Why would you multiply before dividing when something's there to create bigger numbers and you don't have a calculator? Because I'm a silly person. This turns out to be 160 pi square units. That's surface area. Not so bad. So I'll have a couple more videos for you running through. But geez, look at that. Look at that. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 steps if you include writing down the formula. Whoop! Calculus 2! Let's get it! I'll be back with another fun-filled video next.